Okay, so when we talk about the mirrors, you've got pretty much the two equations. The one we just derived and found that the focal point for a spherical mirror is related to r over 2, and that's it. The other two equations that we have to deal with are straightforward. The mirror equation talks about finding where is the location of an image. So when we look at the mirror, some object will exist at some location. It will cast light onto the mirror, which does what it does on the mirror, and it'll intersect at some point, which we call the image. And the image is the thing that you can see. So determining what's the location of this image, or what's the image distance, we use this formula. So 1 over the focal point is related to 1 over the object distance plus 1 over the image distance. And for this, I use 1 over p and 1 over I to define these things. So this will be p, or if you really don't like that, we can call it d object. I think one of the books also calls it like s or s prime, and I absolutely hate that. So here we have I, or if you prefer, di for the image, or I think s prime. And this is why I hate this, because it's just not obvious. The reason we don't call this one O is because 1 over O looks like infinity. So, I mean, we just go to the next letter in the alphabet. So this is the equation, either 1 over P plus 1 over I, or 1 over DO and DI, if you like those a little bit better. Another issue that comes up is the magnification. So the image could be the same size, larger, or smaller than the original object. And that can be predicted by using this formula, which is negative I over P, or negative di over do. And this is it. These are your two equations that you really need to deal with for thin spherical mirrors. The work should be easy for the remainder of this unit, but I suspect it won't be, because there are a couple key issues about how to work with these, and that mostly deals with figuring out the sign conventions. So we'll talk about issues of realness and virtualness and figure out the sign conventions. Okay, when you deal with a mirror, we'll make this the mirror, and I'm going to put the object on this side. We have other things that are on this side of the mirror also. It looks like the center of curvature for wherever the center of this round sphere would be is, I don't know, maybe here. So we'll call that R, because its distance from the very center is the radius of curvature. And then we know that R over 2 is the focal point. So here's another interesting point in this problem. These things have signs on them. So when you guys have like F is equal to R over 2, you need to keep in mind that this could be a positive or a negative sign. And for concave mirrors, and this one's called concave, and the shape means that it kind of caves toward us like that. It's got positive focal points. So the focus here is positive F for concave. When we look at these things and do the math, to figure out what side is positive and what side is negative, I like to use this convention. This is the source of the light, the object. So let the light come in and hit the mirror. And what do you expect the light to do? It bounces off the mirror, right? So if the light comes back, everything that's on this side of the mirror has a positive sign. You know the light doesn't go into the mirror, so anything on that side we'll just say is weird, and we'll put a minus sign on it. So in this case, I have an object that is positive, radius of curvature is positive, which translates into a positive focal point. Okay, so there's a little bit of a hard cut because I invented numbers that I couldn't do in my head easily. So if we want to deal with this mirror, I want to do some math and make some predictions. So in this picture, let's make sure that we do things super properly, right? So we'll make this very thin, and we'll give ourselves a note to remember that this is concave. I want to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's say that here is the focal point at 10 centimeters. And don't ever trust a number that doesn't have a sign on it, especially with geometric optics. Just because this doesn't have a minus sign in front of it does not necessarily mean that it is positive. You should just double check and see, based on, you know, the positive side versus the negative side, is it truly positive? And in this case, we can see, yes, it is. Okay, so if that's 5, 10, let's say at 1, 2, 3, 4, 5. Let's make this the object location. So that'll be, what, 15? And then double that, 5, 10. There's our radius of curvature, which is given as 20 centimeters. So if the object is over here, that's the source of the light. That's helping to define this is the positive side and this is the negative side. The other thing about the object, because it's the defining factor, it's kind of exempt from the rules of plus and minus. It's always going to be considered positive. There's one special case if you have a virtual object where it could be negative, and we'll talk about that much later. It's kind of a special case, not a standard case. So a typical me kind of problem would be, tell me everything possible about this situation. That means find the image location, find the magnifications if possible, and then even comment on the orientation. Is the reflection right side up or upside down? And the realness or virtualness of this, which is a concept that we'll cover when we see it. Okay, so we've got our thin mirror equation is 1 over f is 1 over p plus 1 over I. So we'll just put in the numbers and kind of see what comes up. So here's 1 over 1, or 1 over 10. This is 1 over 15 centimeters plus 1 over I. And I said I was going to pick numbers that were better, and I still didn't do these ahead of time, so I want to make these the same. So I guess maybe I need to find a common denominator and multiply them through. Oh man, that's not great. I guess if I multiply this by 3 on top and bottom, that's 3 over 30. I can multiply this by 2 on top and bottom. Did that work out? Hey, I think it did. And that's not equals, that's plus. So 3/30 minus 2/30, it leaves me to 1 over 30 equals 1 over the image. So that means the image distance is positive 30 centimeters. We should mark that. This is 10 centimeters, 20 centimeters, and I guess 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here we are at our image is 30 centimeters. Okay, the other issues are find the magnification, right? So if our magnification is negative I over P, that's negative 30 centimeters over the object distance, which was 15 centimeters. That gives me magnification of minus 2. Okay, so the other things that we should note. What is there to know? Is this real or is it virtual? So what real means is that you can project it onto a piece of paper. I can take my mirror and kind of play with it and shine it and project the reflection in a place where I can touch it. If the reflection is actually happening here, like in the real world where the light really goes, it's conceivable that I could put a piece of paper here and catch it. So if you have positive images, that corresponds to real images. Okay, what would virtual mean? That would be something that you can't touch. And this is really an illusion or a trick on the eye. If the image happened to be behind the mirror, obviously you can't take a piece of paper and put it behind the mirror and expect to catch the image. You have to be literally looking into the mirror so that your brain can catch the divergent rays and then extrapolate where it thinks the image is. If you have negative image distances, that tells us that the image was virtual. How about the next one? What's the orientation? Is it right side up or upside down? I didn't draw it on here because I didn't know it, right? So what evidence do we have? look into the magnification. And a mistake that students will often make, they see a minus sign and they think the image is smaller. That's not true. The number in front of the magnification, that is how big it is. If it's greater than 1, it's larger. If it's smaller than 1, it's smaller. The sign tells you the orientation. So if I have a minus sign here, it means that my image, yes, this case is 2 times bigger, but it's also 2 times bigger and inverted. It's upside down. So our orientation is inverted. Is there anything else that we can ask about? I don't think so. I mean, what do you have that we could talk about? Find the image location, find its magnification, interpret it, real or virtual. Is it right side up or upside down? What kind of a mirror was it? Well, we already knew that. What can you say about the signs on the focal points? You get that from the shape. I don't think there's really anything else I can ask us in this particular problem. I guess our next skill is, how do we draw a ray diagram? We can use all of the math to figure out these numbers, but we can also use a ray diagram to geometrically show them and show what the image should look like. So when we do some kind of a ray diagram, actually, why don't we just use the previous one that we had over here and kind of fill in the blanks? There are 4 rays that are possible that we can use. You only need 2. If your math or your art skills are really good, all of them will line up. If they're kind of bad, then you'll have multiple intersections, so we don't like that. You only need 2. The different types of rays that we might draw. The first one, you want to come in flat, but then reflect through the focal point. And why don't I shade this one in? This is the red ray. So we want to come in flat from the object's tip. Come in flat to make contact with the mirror. And then we want to reflect through the focal point. So that would be there. And why don't we go a little further just to make sure I got plenty of room. Okay. The second one, we want to aim for the focus and then reflect flat. So I'm going to make a beeline directly for that focal point and make sure that they connect. And recall, this is a thin mirror, so we'll go all the way to the plane and then reflect backwards here. And is that right? Oh no, it's not. I missed the point. And a little bit makes a difference, right? So I'm trying to use grid paper conscientiously to get this right. Yeah, that'll go right through the middle. That's a bad ray. Okay, and then we'll have it come back flat. So you only need the 2. However, there are 4, so you have options. The 4th one, should you choose to use it, aim for the middle. And that doesn't mean the center of curvature. It means the actual middle of the mirror where the axis falls on it. And then reflect at the same angle. So for number 3, I want to make a line and directly connect it here. And then we want it to come back with the same angle. And that can be kind of hard to estimate, but fortunately, I know the slope, right? So this is 4 up. We'll come 4 down and make sure that it connects through that point. Okay. There's angle 3. And the last one, if you are going through the center of curvature, that means the very center of the mirror, then you're following kind of a radial line, right? And a radial line hits the surface normally and then bounces back exactly along the same point. And this one, unfortunately, I don't have room for on the paper. So we'll have to just use our imaginations. Here's a line that connects R to this. The fact that it's back here is okay, right? Because the line will come off of this, but it's really just a straight line that connects her. So let's assume that off the page, it hits this surface and then bounces back. It would follow the same line through R, and then we have some kind of a intersection over here. This is where I say, unless you have drafting software, you're really really careful. I've got multiple intersections here, so I don't know which one's the right one. I can say that the image is pretty close to over here. So we'll label that as just I. And what else do we notice about it? We can use this to kind of measure. I've got the image here at 30 away, which is pretty much what we tried to estimate here. Okay, I've got an orientation that's upside down. That's this. It's on which side? The real side. And it's, what's its magnification? It's this compared to that. That's a magnification of 2. It's twice as large as the object. So there we get that. I don't expect any of us to use the ray diagrams to actually prove any of this stuff, right? But it is good to give you an idea when you do your ray diagram. You know what to look for. You know roughly in what neighborhood is the image. Is it on the positive or negative side, right? That'll help you check your work. You can see, is it going to be bigger or smaller, roughly, right? Or is it going to be right side up or upside down? So these larger features are the real things that we want to get out of the ray diagram. But these actual numbers, do the math to calculate them. I don't expect you to get them right graphically. Okay, and so to kind of reiterate all of these, aim for the center of curvature, and that's R, and then reflect straight back along it. So these are your rays to do a proper ray diagram. All right, there's another example. Actually, there's 2 more examples with 2 possible ray diagrams. So why don't we just practice and try them all? I want to do the same thing, but let's say I've got an object at 10 centimeters and the focal point is at 20. Do the same thing. What's the image location, object distance, et cetera, et cetera, et cetera. So we might try this out first with a ray diagram and then go back and try to prove it mathematically. So we'll draw our ray diagram. The mirror is still concave. And I got what would we say, 10? So let's make this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is our object. And then 1, 2, 3, 4, 5, 6, 7. This will be our focal point. All right, so let's do the ray diagram part first and just see how things work out. And then we'll go back and just double check our work with the math. So my first one, I want to come in flat and then bounce back. So coming in flat and bouncing back, we want to go through the focal point, right? So here. Okay, the other one is aim for F and then bounce back flat. Well, I don't have that one. So we'll have to do something like this. Kind of let it come through. Whoops. And then have to find the plane. It's right there. Try to make sure that it's flat. It's not exactly on a line, so errors here will translate. Okay. Neither of these two intersect anywhere, which is not great. So what we would have to do in this situation is draw what we call virtual rays. Remember, the brain is a little dumb about these things. When it comes into the eye, you just trace it backwards. If we don't have a true spot where these rays intersect, then just continue them backwards until they do intersect, right? So in that case, I guess we'll have to extend. I like to use dotted lines to represent virtual rays, just as a reminder that they're not really here. Oh, and I hope this one will fit on the paper. Oh, barely. Okay. So we have some estimates ready for the image location. It's not here on the real side, so immediately we can see that this image will be virtual. So that'll be the image I. Where is it? I guess we'll have to take some measurements, right? So this is 1, 2, 3, 4, 5, 6, 7, 8. Oh no. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, not good. I was off by 1. Oh, this is going to be not fun to do the math for. 1, 2, 3, 4, 5, 6. That's 10. So this is 1, 2, 3. Looks like it's at 18 centimeters. Just to be complete, some of us might like the other rays, so there's no reason that we have to use these 3. This would be that ray 3. Just comes in and then bounces back. Same angle, so make sure it goes through 1, 2, 3, there. Slightly better picture than I did last time. So that's the real ray, and the virtual comes all the way back, and it looks like they meet without a lot of offset. And of course, the last one, well, I really can't do it, right? Because the center of curvature is off the page. This would be somewhere way out here. So unfortunately, I can't do that one. All right, so what are the things that we got out of the ray diagram? Our estimate, we think I is about 18 centimeters. No, wait, is it 18 centimeters? Because the object defines this side as positive and this side is negative. So this is really minus 18 centimeters. What can we guess about the magnification? This was 4 high, so this will be, looks like 4 about 8 high. Okay, so that'll be a factor of 2. And it's in the same orientation, so it's really plus 2. And what else can we see? We can either see clearly on the picture that it's virtual. And we can also see that the orientation is positive, which is plus here. It's also upright. So these are our guesses. Let's take... Gosh, I really don't want to do it properly. You should do this at home. For you, use 9 centimeters as the object distance. I'm going to use 10 because that's what I intended in the first place. So the formula, 1 over F is 1 over P plus 1 over I, should be, looks like 1 over the focal point we said was not 10, was 20. Equals 1 over the image or object distance, which was 10, plus 1 over I. This we can really say is 2 over 20. So maybe I'll make that correction in line. 1/20 minus 2/20. 1 over I is 1 minus 2 is negative 1 over 20. And that means the object or the image distance is negative 20 centimeters. Okay, how about the magnification? This negative image over object, which is negative 20, over the object was 10. Negative, negative cancels, so that gives me a positive 2. And again, we can say this is upright because of the sign, and it's virtual because of that sign. It'd be interesting, and maybe I'll add this as a still frame at the end. I really screwed this up, and this wasn't the ideal situation. So I'll go back with a calculator and do it with 9 centimeters and give you the true value over here. Okay, well, doing the math with a proper calculator, assuming that this was the actual object distance to match the diagram. So in that case, I get 1 over 20 for the focus equals 1 over 9 plus 1 over I. I get negative 0.06111 per centimeter equals 1 over I. And if we invert that, I get I as minus about 16.36 centimeters. So it's kind of okay, but really not quite that great. It's a little bit off. What were the takeaways? It's still negative on the right side, and it's still, well, when you do this through, we'd find out what the magnification is also. Yeah, and I think our magnification would be, 1.6. Okay, so there's 2 cases. And what did we notice in each one? What was the real difference? Here my object was outside of the focal point. And what did we get as a result? We got real images. Okay, and real images with, what we say, magnifications that I can't say anything about. So all the images here were real and upside down when the object is outside of the focal point. When we come a little bit closer and bring the object inside the focal point, it changes the way these things interact with the surface and causes an inversion. So now we get virtual images, and they happen to be upright. This type of mirror is a shaving mirror or a makeup mirror. It's a magnifying mirror, so we assume that your face is inside the focal point, so they design it that way, and you get blown up, larger, magnified virtual images, just like the images you get when you stare into a bathroom mirror. Okay, the only difference is they're magnified, not straight. So this same type of mirror will give you 2 different results depending on how you use it, and that's based again on the object location. Well, what other shape do we have? We've got the convex mirror. So why don't we do the same thing? Hopefully these numbers will be decent. Making them up on the spot. We'll say P is 20, and how about my focal point is, I don't know, let's say 10. And I want to do focal point of minus 10 because it's convex. So I'll make sure I have enough room. This should probably be okay. And count these appropriately. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's a 10. 1, 2, 3, 4. There's a 20. F equals nothing. There's no F there. Okay, and we'll just again say convex, and then 1, 2, 3, 4, 5, 10. So that's the focus. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this will just be 20 centimeters. Because you never know. I want to give us some room to work. Okay, so my object will make here at plus 20, and the focus is over here at minus 10. In the ray diagram, it goes the same way that it did the first time. I want to come in flat, but then reflect back through the focal point. And there's a slight problem because the focal point isn't on the same side. So how do we reflect through it? Easy. Just make sure that your line of reflection goes through the focal point. So it happens to be behind it. That's fine. We'll do that. And we'll trace this back as a virtual ray just in case. Okay, the other one would be, I think, blue. How do you go through the focus and then reflect flat? I'd say aim for the focus, right? So make a straight line from the object to the focus the best you can. And then here, as soon as you hit the mirror, you have to flatten out. So we'll flatten it. Okay. If we wanted to, we could make the second ray. I think it was over here, right? And then the same angle would be 4 down, so there. All right, and the last one was what? Aim for the center of curvature, right? The center of curvature is double the focus, so R is way back there. I would want something that goes straight to the surface and then bounces off at exactly the same angle, which we would draw backwards like this. So it's a decent picture. And it looks like my object or my image is over here at, about, looks like 1, 2, 3, 4, 5, 6, about -7. So my guess is the image is about -7. About the magnification, it's about 1.5, so a little over a quarter. I don't know, maybe we'll say about a third. Positive 1/3, right? Because it's a little bit smaller and it's upright. So if we wanted to kind of go through and now prove these, oh, what else are we seeing? We're seeing demagnified. We're seeing virtual, and we're seeing upright. So to do the work, I got 1 over F. Remember, the focus is negative this time. 1 over 20 for the object plus 1 over the image. And again, we want to make some corrections so that these are comparable. How about we make this 2 over 20 to represent 1/10. I got 2/20ths. I want to take away 1/20th, so I guess that's no, I got negative 2/20ths minus another 1/20th, so I get minus 3/20ths equals 1 over the image. So the image is, I don't know, I'll leave this up to you. What is that? 7, 14, 21. I'm using some guessing. It's a little bit under 7. Figure this out in decimal and get back to me. The magnification would be minus I over P, which is negative 20 over 3, divided by the object distance, which is 20, equals negative 1/3. And what's wrong with that? This image distance, dang it, is negative because of that minus sign. So negative 20 gives me that. Pretty good guess on the magnification. I don't know how good of a guess on the image distance. You have to look it up on your own. Realistically, with this ray diagram, what do we see? I've got a mirror that demagnifies always. And I don't need to draw another diagram because if I bring this closer, will I ever get inside the focal range? No, I won't, because it's on the other side of the mirror. So no matter how I draw this from 0 all the way up to infinity, it still looks the same. So where would you see these in practice? Any kind of a situation where it's useful to make the images smaller on the screen. So I can think of one case. I haven't used it in a while because we're in quarantine, but if I wanted to see more of the road behind me, I might use a convex mirror as a rear view mirror, right? Something that would cover more of the distance behind me, reduce my blind spot, and get more of that image smaller and thus crushed onto the viewing area of the mirror. These can also be used for surveillance. So if the convenience store is too cheap to get a video camera, they can put a giant spherical mirror up in the corner of the store. And in the reflection, if it's small enough, you cram all of the store's object area into the mirror. So that might be another good place that you would use those. I can think of in hospitals, they also use these kinds of mirrors for corridors at the intersections. So when you're walking, you can take a look upward and see, is anyone coming on a speeding gurney? Because you don't want to get taken out if someone's coding and a doctor and a crash team are on their way. So it's just a great way of taking a lot of visibility, crushing it into a smaller space, and taking advantage of the fact the images are demagnifying. Before we get too far with that, we should go back for the mirror that was convex. We noticed that it has the effect of making the images smaller so you can see more of them. But that also kind of screws with the human brain a little bit, because if the image looks smaller, then we assume that it's further away. So you might notice on these kinds of mirrors, they're marked. Objects in mirror are closer than they appear. And they have to do that to idiot-proof it, because they can't say at the bottom, hey dummy, the focal point is negative, do the math. Right? So this is a case where there's a trade-off. To get more stuff on the screen, the images are smaller, but that also makes them look like they might be further away than they really are. So you just have to be kind of aware of that when you use this mirror.